Alright, so today we're going to look at kind of a historical view of the development of mathematical tools. And we're going to look at this from a point of functionality. We're going to look at the tools that were developed for a particular set of functions. So let's see if I can get this to sign up here. There we go. So what we want to look at is how the concept of counting and naming numbers turned into a writing system. And then we're going to compare writing systems to see them aid in calculation. Now, most of the story of numbers that we get are from the Greek to Roman to European dialogue, and we see two types of number systems that dominate and are still in our Western culture, which are Roman numerals, which are based off of the tally mark system, and I did this in a previous lecture, where this is 1, this is 2, this is 3, 1 before 5 is 5, 5, 6, 7, 8, and 1 before 10 is 9, and 10. And the symbol has a value, and you add up how many times that value appears, except for these special preceding symbols. And this is not in all of Roman writing. This was a later invention, and I think we can hear how it comes: 1, 2, 3, the 1 before 5, which would be 4, 5, 6. Well, 5 and 1 is 6, 5 and 2 is 7, 5 and 3 is 8, the 1 before 10 is 9, 10, and so on. And so they use this additive nature of generating numbers. And many cultures, actually, that's the first type of numbers that they develop. But we use a number system that uses bases. And so we're going to look at bases, and we're going to look at it from our number system. And then we'll go back and we'll explore other cultural number systems that appear in the world. Now, what we mean by a base number system, and if you watch the video in the discussion board, we talk about the development of this. In about 1202 AD, Fibonacci published a book called Liber Abaci, and in it he represents the 9 Indian fingers and the Persian Zephyr for 0. And he lays forth that you could talk about any number with this. Well, the thing was, 1202 AD is when this enters Western culture, specifically Italy and the merchant class in Venice. But it was present in India 500 BCE. And in 500 AD, we know for sure that Indian mathematicians were using the concept of numbers that we currently use now. And we're going to compare base systems, but to talk about a base, we wanted to kind of take apart our number system and see what it's functionally doing. So previous number systems, you had to add every named component to get the value of what was coming. In our number system, we have a base that can have the digits 0 through 9. And the digits 0 through 9 can represent any value for 10. Well, what we then do is we let the place value, where it is written, carry extra information. And so if we were to break this in components, we say the name 1000, we say the name 200, and we say the name 4. But the place values that have these only have one digit in them. And so we have a way of converting the place values digit into its actual numerical value. And to do that, we need to have the idea of base and exponents. And so first we're going to do a little review of exponents and how exponents will help us with the base. And so what an exponent is an exponent is a way of writing multiple multiplications. And so if we have multiple multiplications, 3 times 3 times 3 times 3 times 3, I'm going to count them, 1, 2, 3, 4, 5, we write this as 3 to the 5th. And so it's a way of talking about multiple multiplications. And so let's see, 3 times 3 is 9, 27, 81, what is that, 243? And you'll find in our notations, mathematicians in essence are fairly lazy. I have another video I think I'll post at some point about how mathematics is the idea of trying to do the least amount of work to get the most utility out of it, looking for the pattern that saves you the most time. And so what we're going to do here is we're specifically going to look at bases where we can exploit exponents. But let's just take the idea of exponents in its most generic form and see what we can do with it. So we have some base, and you'll see the word base gets said a lot. It's the lower part of the number. And then we have the exponent, or the power. And they can be any number. We will talk about these being integers, 1, 2, 3, 4. And this is equivalent to multiplying the base n times. And there's some neat things that happen. We will say this is b to the nth power. And there are some neat things that happen. So if I have b to the first power, I get b times b times b, which is just itself. Here comes the neat bit. If I have b to the 0 power, well, I have a series of multiplications with no b in it. But in front of all multiplications, we can think that there's a multiplying by 1. So if I'll take that 1, and then I'll put 0 b's to it. And so anything to the 0th power, notice I said 0th power, is equal to 1. And this is going to help us. Well, another thing that can happen is multiplication has its inverse. I can reverse the process of multiplication, and I can divide. And we show that in powers by having a negative exponent. Having a negative exponent means that I bring it downstairs. I always think of the negative sign as hooking it downstairs. And so I start dividing by how many times I see that. So b to the negative 2 would be 1 over b squared, and so on. And these ideas together help us write any number with just these 10 digits. And I really would like you to think about the video in the discussion that comes out, and the questions Indians were asking to make them develop this system. And it was questions that the Romans weren't asking. And it shows how mathematics exists inside of the cultural references at the time. So let's take our bases and see what we can do with it. So if I take the number 663, that's the same as 600 plus 60 plus 3. But I'm going to focus on tens in here, because I can say this is 6 times 100, because that's the hundreds place, plus 6 times 10, because that's the tens place, plus 6 times 1, because that's the ones place. Well, I can do all of this in terms of my base. I can do 6 times 10 to the second power, plus 6 times 10 to the first power. Whoops, that's not 6, that's a 3. My bad there. Plus 3 times 10 to the 0th. And so we can think of each place in our number system as being holding the multiples of 10 that we're going to use to add up our number. And so with our decimal place, immediately to the left of it is 10 to the 0, 10 to the second, 10 to the first, and 10 to the second. And so that's the ones, the tens, and the hundreds. Then we usually separate by groupings of 3, the thousands. That would be 10 thousandths. That would be 100 thousandths. And then that would be a million. And so I put those commas in to separate. And so that's a million. And that's 1,000. But this gives us a way of only using 10 characters to write any number. And this is the key to this invention. When we look at other base systems, even the Roman numeral systems, if we have a minimal amount of characters, and we'll see that we can write any number with the Roman system, but it doesn't progress as neatly as this. There's some neat things that happen. For example, if I look at, let's take 663, and if I were to add 1 to it, and keep adding 1 to it until I've done it 7 times, I will have run out of my 0 to 9, and so I get my digit here, and that extra digit scrolls over and increases. And so the ability for these to kind of work like counters, and when you fill the space, it increases the next space, helps us calculate with these numbers. And we'll look at the calculation forms in our base system. But this is called a positional value system, or place value. And the form that we are writing in, when I write out the actual value associated with it, is called the expanded form. So let's take all these concepts, wrap them back together again. So I have 4 digits, and so this digit is in the thousands place, and so it's 10 to the third, and I have 3 times 10 to the third plus, and this is in the hundreds place, so that's 4 times 10 to the second plus 0 times 10 to the first plus 7 times 10 to the 0. Or 10 to the 0. And these tell me that I have 3,000 plus 400 plus 0 plus 7. And this is almost reads off like I say the number, 3,407. And this positional value system will give us the ability to also do quick additions and multiplications. Now let's compare this to the Babylonian system. The Babylonian system used bases of 60. And they used that because 60, they divided a circle into 6 60s. That's where we get 360 degrees from. And they were avid astronomers, and so circular motion and breaking apart the day became very important. What's nice about 60 is there are a lot of useful fractions in 60. In fact, if we look at the face of a clock, we get, the twelfths. And old school multiplication tables used to go up to twelfths because there's 12 inches in a foot, 12 months in a year. This base 60 system kind of permeates through our culture. And so what the Babylonian system would do is each positional value would be 60. And so we would have 60 to the 0th, or the ones place, 60 squared, which is the 360, 60 cubed, and so on. And then the symbols they had was for 1 and 10. And so I could write a number in the Babylonian system. So I could write these three positions. Notice how they're separated by spaces. And so this is 2, 11, 22. And if I bring that down, it's 2 times 60 squared plus 11 times 60 to the first plus 22 times 60 to the 0. And 60 squared is 3,600. So this is 2 times 3,600 plus 11 times 60 plus 22 times 1, or 7,200 plus 11 times 60. What is 11 times 60? 6 times 11 is 66, a 0 on the end, 660 plus 22. And so adding them up, that's 7,882. Right? 2, 8, 7,822. And so we find this on some of the earliest written mathematics in Babylonian times. And this is a positional system with only 2-character representation. But it becomes a very kind of unwieldy with the base 60 numbers. And one more I think we'll look at here is going to be the Mayan system. Mayans are also astronomers, and they were fascinated with Venus. And Venus has a odd pattern of cycles with the Earth. And there's been a lot of look at the Mayan system, but it has a base and it's astronomy and a base 20 system. And let's pull back here. Give me 1 second. Alright, and so let's get my screen here. So the Mayans had a pictograph system, which was etched into stone. And so these things were a little easier to etch into stone. Or at least I've always seen it etched into stone. They might have had a papyri or paper system, but I've always seen the stone carvings of their calendars. Notice how the number 5, or the number of fingers on one hand, play into here. And so you can think of this as pulling up fingers, grabbing a full hand, a hand in the next set of fingers, and then in both hands, and I guess toes, which the Celts and the French numeral system counts up to 20. That's why we still have the idea of the score in the English system, which came actually from the French and Celtic. And so we have names up to 20. That we name the teens differently than we name higher numbers, because we counted with our toes and fingers. And so there's a pattern. Whoops, I added one too many lines here. Each line representing 5, and then in the dots, adding on top of it. And so we have a base 20 system. There are 20 symbols, and the 20 symbols means you have your base. And so notice what we did in our systems. We've had a base where we could count up to the base in an additive system, like the Roman system where you added the different numbers and there were different symbols for different values, similar to the Babylonian system where there were 2 symbols but they would not count more than 60, or the Indo-Arabic numbers where there were a set amount of symbols that determine the base. And the Mayans is like that. There are 20 symbols that determine a base 20. And so I could write a number in the Mayan system where they work from the top down. So they would write, this would be carved downwards, and it would represent a number. And so 1, 2, so 0, 1, 2, 3. And so this would be 14, right? Because there's 5, 10, 4. 14 times 20 to the third. 0 times 20 to the second. And that's what, 7 times 20 to the first. And 7 times 20 to the 0. And so if we add that, let's see, 20 to the third is 7,200. Notice how that pattern of 360, 60 times 2 is in here, and 20 squared, what am I missing here? I am missing something small here. Oh yes, that's right. They didn't use a direct base system. Let's see, 20 times 20. They used 360 here, which is 60 times 6, which is 20 squared minus 2 times 20. And let's see, 20 cubed would be 8,000. So now they're minusing 20 times 40. And so there's a subtractive on this. My apologies. When you study different numerical systems, you'll find that there's different little patterns that they have in representing them things. And most of that was usually around the machines they used to calculate. And yes, machines. We have used machines to calculate throughout history. The Incans and the Mayans had systems of knots, very similar to the abaci. And in Rome, they had little counting abacus, or even little gears that they would count on. And in medieval times, we used counting boards, which in the video you'll see examples of. And so sometimes these bases tie back to the machines they're using. And notice there's a leeway here. There's a deduction before you make it around each number. And a lot of that has to do with how sometimes 0 was not immediately taken by a culture. With our number system, because 0 was immediately taken into the Indo-Arabic number system, the 0 place value works fairly well. And what you can find is you could have an additive value if you didn't have the concept of 0, where you took the upper end of this would work into this. And a lot of these number systems existed throughout a long history where they changed over the time, and we are referring to usually the most recorded. And don't worry, what I want to see is how hard or easy it is to write in positional systems. And so here I have 7 times 1, which is 7. I have 7 times 20, which is 140. I have 0 times the 360. And then I'm going to have 14 times the 7,200, which is 100,800. So I add these all up. Whoops, that's 800. 7, 4, 9, 100,947. And so different cultures invented ways of writing bigger numbers by using where you wrote the number, where it was written, in the order of the number, as having some value in place. And we're going to find that in the systems we currently have, that lets us do calculations fairly easily. So play with some of these systems. I'm not expecting you to memorize the bases of the Mayan system. I can't memorize them, but if we can look them up, we can convert back and forth. Because base systems become very, very useful. Like I said, it was tied to the machinery for calculating. Well, we live in a modern time where the machine I am talking to you on has a base of 2. Though it's nice sometimes when we can program computers in bases of 8 or bases of 16. And so these number systems actually get used by computer scientists often, as it's easier to work with the machine. In fact, it will also give us some techniques for doing multiplication and division that aren't the same that we use in our base system. And that's what we're going to explore as we explore Chapter 4.